Hello, everyone. This is Chaoji. I am from Rutgers University. I am glad to present our paper, SPINE, Scaling Up Programming by Negative Example for String Filtering and Transformation. In this work, we focus on the massive textual data wrangling problem. According to the New York Times report, data scientists spend 80% of their time curating the data, remaining 20% for data analysis. Of course, we can write some programs like the Python scripts to process the data. But the challenging is that 99% of the end users are not programmers. To solve such a problem, researchers proposed a new technique in the recent years, programming by example. So what is programming by example? The general idea is that we can learn some program automatically from the given input and output strings. For instance, here we have two input and output examples, and our target is to extract the initial of the input strings. And based on these strings, we can have a synthesizer to learn two consistent programs. The first consistent program will concat the first char of the first word with the first char of the second word. And the second program will concat the character W with the first char of the last word. And in the second part, we will have a ranking algorithms to help us pick the better program. And in this example, we can see the first program is more general than the second one. So we will pick the first one. And this programming by example technique can be applied on several data wrangling tasks. Once we have some example strings and we have some potential consistent pattern behind our strings. So now let's take the string filtering as example to illustrate the detail of programming by example. In string filtering task, we need to learn some patterns matching all the given strings. For example, here we have 4 strings for websites. And we can see they have some patterns behind these strings, that all of these strings are formed by 3w.letters.letters. So to get these patterns, the first thing we need to have is to define a domain-specific language. And the idea is to use tokens match specific substring using regular expressions. For example, here, the token T alpha will match the alphanumeric letters and will match the 5kg or ID. And we will have several different tokens. And in the second part, to represent all the consistent patterns in polynomial space, we need to build a directed asynchronic graph DAG on the original string. For example, we can transform our string 5kb to a graph with vertices and edges. And in this DAG, the 0 represents the start position of the string, and the 1 represents the first position of the string. So the edge 0, 1 will represent the substring 5 of the original string, which is a digit letter, and it will match the token TD. So in this way, we can build a DAG for every string. And a DAG represents the patterns for one string. And our target is to find the consistent patterns among different strings. So we need to use the DAG interaction operation to generate a new DAG containing all the common edges. To do so, we need to enumerate all the vertex pair and traverse all the edges among these vertices and keep the edges with the common labels. For example, here we can see the edge TD appears in the first DAG and the second DAG. So we can keep it in our new result DAG. And in the same way, we can traverse all the edges and keep all the common edges appears in both the DAGs. Now we have a DAG containing all the common informations, and we need to pick one program among all the consistent programs. We can apply some greedy algorithms to achieve this. For example, suppose we have a path goes through the vertices 0, 0, and 1, 1, and 2, 2, and it contains 2 tokens, TD and TU. It will match the 5K of the first string, and it will match the 1B of the second string. This is the classic programming by example framework, but we found that they have some limitation on this work, that they have some limitation on supporting the negative examples. The FeedX, which is a classic string filtering framework, it do support the negative example, but it had a bad scalability. You need to replicate all the edges and vertex during the synthesis. So it has a scalability n to the power of n squared, where n is the length of the strings. And for feedbacks, the graph will grow exponentially. Another work, flash fill, which is a classic string transformation work. It cannot deal with the negative example. So if we get a wrong transformation program, we have to correct it manually by entering a new positive example. Wondering that if we can take a use of the negative information, we just need to click the incorrect one, and it can automatically refine a new consistent program that satisfying our requirement. So based on our observation, we propose our work, SPY, which has a new synthesis algorithms and a new search algorithms. And we apply our SPY on two task wrangling tasks, string filtering and string transformation. So in SPY, there will be a new kind of tag, negative tag, to describe the information for negative string. For example, here we have a negative string R, which have the string F1. We will build a new tag for this one. And then with this negative tag, we can do the subtraction between positive tag and negative tag. This subtraction operation contains two steps. The first step is to copy the positive tag, because our new tag is based on our positive tag. And the second step is to enumerate all the edges in the negative tag and check whether it appears in the new tag. For example, here we can see the token T alpha appears in the negative tag as well as in the new tag. So we know that this contains the negative information. So we need to mark it on the new tag that contains the negative information. And now we will change its token to with a new tuple R02, representing that this edge also appears in the negative tag from the position 0 to 2. And in the same way, we can see that TD also appears in the negative tag and the new tag. So we're also using the same way to mark it as the negative edge. In this way, now we have a new tag that containing all the positive information, also containing all the negative information. Now we can find a consistent program using this tag to find a valid path. The valid path is a path not matching any complete negative substrings. For example, this path goes through the vertex 0, 0, 1, 1, and 2, 2, contains the token TD and TU. We will match some substring of the positive strings, but it will not match any substring of the negative string. So this is a valid path, and this is the path we want. Another example is that a path goes through vertex 2, 1, and 3, 2. It will match an uppercase letter. So it will match some substring of the positive strings, and we will not match any substring of the negative string. In the construct, this is an example of an invalid path. This path goes through the vertex 0, 0, and 3, 2. It matches the alphanumeric letters. So it will match the whole string of the negative string. So this will be an invalid path. And in our work, we design a dynamic programming algorithms to find the optimal valid path among all these possible paths. And we avoid traversing all the pairs of edges. And this work can be easily extended to the string transformation task, because the string transformation task just have some tiny difference on the domain-specific language and the synthesis algorithms. Due to the time limitations, we will not introduce the transformation in detail in this presentation. And now, thanks to our experiment, we have two experiments, one for string filtering and one for string transformation. In the string filtering experiment, we use the benchmark from Rutgers, and we compare our work with the FIDEX and NFA. NFA is a baseline based on the finite state automata serial, and we achieved the lazy determination to improve the efficiency for NFA. For the string transformation task, we use the benchmarks from the PROS benchmark provided by Microsoft Research. And we compare our work with the flash fill and blink fill. This is the first experiment. We evaluate the DAG operation efficiencies. In the diagram, the x-axis represents how many examples we use. For example, the 2,8 here means that we intersect two positive examples and subtracting it with the 8 negative examples. And the dark area here represents the synthesis time, and the light area here represents the search time. We can see the SPI is much faster in the operation because for SPI, the subtraction operation is very efficient. It just simply marks the negative edges during the subtraction, and it lazily determines the value path until the searching. And in the search, it does not need to access many consistent programs which are dominated by other better programs. So in total, the SPI has a higher efficiency. And the right diagram shows the graph size. We can see the SPI has the smallest graph size. This is because in the subtraction operations, the SPI does not need to increase the graph size. But FIDEX will increase much more edges. We can draw a conclusion that our SPI have less running time, smaller graph size, and better scalability. And this is the precision experiment for string filtering. The precision is defined by the corrective filter number divided by the total number of strings. And we can see from the diagram that SPI has much higher precision comparing to NFA and FIDEX. This is because the SPI can find better consistent programs. And this is the experiment for string transformation. The left diagram shows how many examples each method leads to solve the benchmarks. And the right table shows the result for 67 hard transformation benchmarks. The most important thing here is that we can see the SPI can solve more benchmarks comparing to blink fill and flash fill. This is because in this benchmark, the number of examples is limited, and blink fill and flash fill cannot solve the benchmarks using this limited number of examples. In the contrast, the SPI can take a use of the negative information. So if it has some wrong transformation, it can learn from this wrong transformation, and it can use the negative information. We can see that the SPI is faster while using fewer positive examples. Here is our conclusions. In this work, we're scaling up programming by negative example, and we propose a novel synthesis algorithm to process the negative examples. And we design a new dynamic programming algorithms to search the optimal program. And we apply our framework on 2 text wrangling tasks. And our experiment shows that our work outperforms the existing methods, and we have a better scalability. That's all. Thank you.